Welcome to a lesson with Dr. Powell. Let's take a look at the Mobius function and how it can help us find sum and solutions. First, its definition. We're going to output -1 to the k, where k is the number of distinct prime factors of n. Output 0 if it happens to have a square factor. So for instance, let's take mu of 6. 6 is 2 times 3. There's 2 prime factors, so this is -1 squared, +1. If we take mu of 30, this is equal to mu of 2 times 3 times 5, which is -1 cubed, which is -1. Mu of 18 has 9 as a factor, which has a square, therefore output is 0. Mu of 1 is -1 to the 0, since there are 0 prime factors. And there's no square factors, so this is just +1. Okay, now how does mu of n help us to count things and find a sum and solution in a poset? Particularly, it helps us in a factorization poset, or a poset of factors of a number, where each arrow represents is a factor of. So, 6, sorry. 3, 6, and 2, and 1. And then like that, where when we draw these arrows in this Hasse diagram, we do so so that every time I have the relationship, something is a factor of something else, there is an arrow path. And I've done it with a minimal number of arrows. Notice there's no arrow from 1 to 6 because I have an arrow path this way. Those conditions guarantee that I have a Hasse diagram for my poset. Now, and I also need to eliminate the idea that there's any self arrows, and then I have a Hasse diagram. Okay, so that's just implied that it's just a factor of itself. All right. Now, notice the top part of this Hasse diagram is a diamond shape in structure. That looks a lot like a power set poset. So that the contributions of different things to the top are as follows. This 3 at the bottom contributes, or kind of at here on this diamond shape, but it contributes a +1 to the top. We thought about a standard basis with a 1 here and zeros elsewhere. And so we would have a 3, and then we'd have a, if this was my poset in particular, and I'm trying to find a sum and solution of it, then the top part would be would have a 3 times a -1 contribution to the top sum and. Now at this level, I'd have, or actually a +1, sorry, a +1 contribution to the top. At this level, I would have a -1 contribution. And at this level, I'd have a +1 contribution. Now, what about below, down here? Would I have any contribution from these guys? Well, they're outside the diamond. And actually, they're within their own diamond. And the solutions here are self-contained, and they don't exit a power set poset part of this overall set, which means that these have no contribution above outside this diamond shape that's down here. Therefore, we shouldn't get any contribution, and this should be the result, which we can compute as see, -15 and 18, that's +3 plus 3, so 6. So we should have a top sum and solution of 6. We can double check that if we want. We think 1, I need a 1 here to get a 2. Here I need a 2. To get the 6, let's see, I have 2, 1, and 1. So I need a 2 there. And here at this location, let's think what's below the 9 is just the 2 and the 1. So it should be a 6. And then if I add these together, I get 6. So 10, 12. So I should get 6. Top sum and solution was 6. Notice how I got it simply by focusing on the top diamond shape and thinking about the contributions of each part to the top. If I think of these as being sums. Now, in general, this picking out of a diamond shape and these plus ones and minus ones are actually taken care of by the Mobius function in the following way. What we could think of is if we look at our factorization poset, so 18, 9, 3, 1, 2, 6, and 8. If we looked at all of these and thought of putting an 18 in a numerator above everything, we'd actually see the top diamond shape upside down as follows. This is 1. This is 3. This is 2. And I'm going to think of this as being empty set, no primes. This is being 1 prime. This is being 1 prime. And this one down here is 6, which factors as 2 times 3, 2 primes. Notice I have this upside down diamond shape for a power set poset. And since it's symmetric, it picked it out. The Mobius function will pick this out if I take the Mobius of this guy of 1. I take the Mobius, I get a contribution of plus 1. And that's what this says. It says plus 1 contribution. 18 over 9, what's the contribution? Right here, take the Mobius function of 2, you get a -1 contribution. Similarly here, a -1 contribution. This guy over here with 2 prime factors, you get a +1 contribution. Now, what about down here? Well, see, this would be like 9, so it'd be like a repeated prime factor, which looks like a multiset, not a set, not a part of a power set. Out you go. It's not counted, so we say it's 0. It's not part of the diamond shape. So anything outside of the top power set poset structure will be given 0. And that's what happens when things have factors that have squares in them when we do 18 divided by that number. And so in this way, the Mobius function can actually pick all that out. So in general, what we could have said is we could have taken our factors, 18, 9, 6, 3, 2, 1, multiplied each one respectively by the Mobius function of the number underneath, the 18, times mu of 18 over 9, times mu of 18 over 6, times mu of 18 over 3, times mu of 18 over 2, times mu of 18 over 1. And if I added these up, these guys are zeros. This, this one gives me a +1. This gives me a, this one gives me a -1 because it's 3. This one right here gives me a -1 because it's 2. This one's 6, so it gives me a +1. This one gives me a +1. And notice, and in multiplying these and adding, I end up getting 6 as desired. Notice that the Mobius function can take care of all of it for me without actually ever drawing out this particular set. Thanks for watching.